Good morning, everyone. Thanks for coming to this session about single-piece gas quenching and how it can help correct distortion failures in hardening processes. My name is Don Marteeny. I'm Vice President of Engineering at SECO Vacuum Technologies. I'm glad that you could come today, even though we may not be in person. We'll get the chance to discuss some exciting new topics in both heat treating and other heat treating related topics. But before we do, I want to spend just a moment to tell you a little bit about myself. I've been with the SECO Warwick Group since 2008 and SECO Vacuum Technologies since 2017, with a small absence in the middle. During my time here, I have served as project engineer, project manager, and managed various different functions within the business. Today, my responsibility is not only engineering, but project management, field service engineering, and various other business-related functions. I have a bachelor's and master's degree in mechanical engineering from Penn State University, University Park, and I'm a registered professional engineer in the state of Pennsylvania. With that, let's get started. Before we get to the details, I want to give you a brief overview of what we'll talk about during this discussion. First, we'll look at batch processing and the associated equipment, along with the challenges that come with trying to harden materials in a batch processing environment. Then specifically, we'll spend a little bit of time looking at distortion and the issues it causes and how we address them in the batch processing environment. Then we'll look at a traditional technique used to overcome this, and then furthermore look at a modern alternative to that traditional approach. So vacuum batch processing is the established method and preferred method in industry of handling a variety of different processes. As a matter of fact, it well supports a variety of different processes, metallurgical processes, including hardening, case hardening, annealing, tempering, sintering, brazing, and many others, which makes it a fairly versatile platform. Also, since it's the traditional approach to these processes, there's a wide variety of different equipment options available from multiple different manufacturers and with multiple different advantages or strengths. Also, it's easy to make this design accommodate a wide variety of part geometries, weights, physical sizes, and material types. However, those good features come with some specific drawbacks. First is when the parts are loaded into the furnace, naturally we're putting several into the furnace at once, which means the furnace has to be tuned to handle that entire batch. Because of that, not every part receives the same treatment, if you will. So there is part variation or result variation within the batch itself. And we'll look at the details to this in a moment. Also, we have to treat each batch as an individual. We can't treat each part as an individual. What do I mean by that? Well, because each part sees its own unique experience when in the furnace being treated, each part has a slightly unique set of mechanical properties or metallurgical properties that are achieved that vary between its neighbor in the batch. This makes it impossible to trace every part individually. The best we can hope for is to trace each batch by itself. Also, to accommodate the wide variety of geometries and sizes and material types, we have to be able to support them in the furnace. Okay, that's not a problem. We can do that. But what it inadvertently does is increases the cost required and the infrastructure required to process those parts. And what I mean is tooling. We have to have parts that will, tooling that will support the individual parts in the batch in a way that allows them to be efficiently processed. And that tooling, by the way, is typically a wear item. It can only withstand so many processes before it is either disfigured, meaning it's deformed to the point that we have to repair it or replace it, or it becomes damaged just from wear. And moreover, in this whole scenario, when we look at hardening in particular, distortion is the key issue because of the variation in a single part's process experience, if you will. Distortion changes from part to part within the batch. And we'll talk a little bit more about that here in a moment. Before we examine distortion further, though, we need to take a moment to understand the equipment that's being used. There are two types of vacuum furnaces that are used for hardening. One is a single chamber vacuum furnace using high pressure gas quench. Now typically the part is placed in the heating chamber where it goes through a heating process, then is quenched using a gas media like nitrogen in that same position. Then we also have a multi-chamber furnace. Many times these are oil quenching furnaces, but they don't have to be. They could be a gas quenching furnace too. The one shown is oil. But here, instead of the heating and quenching cycles happening in the same chamber, the batch actually processes through a heating and quenching chamber separately. This allows for the oil vapors that are produced during the quench to be managed without damaging the internal portions of the heating chamber itself. Both of these furnaces are capable, and we'll show in a moment a bit more how they're capable. So, what's the problem? Why is distortion an issue? The reason distortion is an issue is because of property non-uniformity. Well, what do I mean by that? Well, I mean that in each batch, parts are arranged to maximize the use of the furnace. What do I mean? Well, they're positioned in the furnace like is shown in the photo, where they're close to one another, and the flow of the quenching media has to go through the batch. What does this do? Well, it depends on the furnace type. In the case of a high pressure gas quenching furnace, the flow goes completely around the outside of the batch in the furnace. So as you'll see here, indicated by the blue arrows, the flow of gas is completely surrounding and impinging on the outside of the batch. Then it goes through the rear of the working or hot zone of the furnace into a heat exchanger, a blower, and then back around the outside of the hot zone. What does this do? Well, it allows for direct impingement of the gases on the outside of the load. Now, most designs have features that improve the flow path to ensure that each part is receiving gas that is both low temperature and high velocity to maintain the overall heat transfer ability of the furnace itself. How? Well, let's take for instance the fact that the blower can be up to 600 horsepower in this case. Or that we can use pressures up to 25 bar of different gases like nitrogen or even helium. This allows for more gas to be closer to the surface of the parts, allowing for more heat transfer from the parts to the gas. Also, this allows for a high velocity at the exit of the nozzles going into the hot zone. This nozzle velocity, which is many times between 40 to 50 meters per second, which by the way is around the wind speed of a Category 3 hurricane, allows for deep impingement, infiltration of the gas flow into the load. Even with all these measures, we still have flow interruptions. To overcome this, you may think that, well, wouldn't it be better to switch to a liquid? That would improve the thermal conductivity of the media directly in contact with the part. Well, yes, it would. But in some cases, it may actually improve it too much. So we're still limited by the material and geometries that we're processing. Also, we don't fully eliminate the flow problem, because here, in this case, instead of the gas is coming from around the outside of the load, the oil is being directed up through the middle of the load from top to bottom. So we still have a variation of temperature and velocity of the oil as it moves through the batch, meaning that not all parts in the batch see the same conditions. Also, in this case, even though it's a low vapor pressure oil, there's still the concern and certain potential and possibility that vapor bubbles will form around the parts as they're being quenched because of the rapid boiling occurring. Of course, the furnace is built with features to mitigate that formation of vapor, but it doesn't stop it completely, and of course that will also slow the heat transfer rate. This flow variation results in different surfaces of a single part cooling at different rates. When this happens, an internal temperature difference between one surface of a part to another occurs. Let's take this gear for instance. This flow variation has caused a 900 degree Fahrenheit temperature difference from one surface to another. Now, as you can imagine, the surface on the outside that is cooler is cooling and contracting much faster than that which is still warm. What does this do? It creates stress within the part, and that stress has to be released in some manner, and it's released as distortion. Now, in some cases, this is okay. The level of distortion that occurs is acceptable in a batch setting. In others, though, it may not be. So that leaves us with an issue. How can we quench and harden parts with difficult geometries like a gear and still meet a distortion specification that requires tight tolerances? Okay. Your first answer may be, well, we can fixture it slightly differently to try to improve flow. Maybe we can find a way to hold them still so that they don't distort. Yeah, that's all possible. And maybe we'll improve it, even in the batch setting. But to truly maintain the shape, we can't do that in a batch setting. Instead, we have to do one piece at a time. Now, one piece at a time, what does that mean? Does that mean quenching in oil? Does it mean quenching in gas? Not sure. So it turns out, though, that industry has already come up with an answer to this. And that answer is press quenching. So how does this process work? Well, first the parts are put into a reheat furnace. Then they're manually transferred, usually by a person, an operator, to the press quench machine. In that press quench machine, the parts are set in a die that is then encapsulates the entire part, and the part is immersed in oil for quenching. This die prevents distortion by simply holding the part in place. Once this is done, the part is removed from the quench machine and taken for a post-wash. Okay. Does it work? Yes. Yes, it works well. Is it difficult? Yes, very. Why? Because, one, safety reasons. This involves the manipulation of a hot part from one furnace to the press quench machine, usually by a person or an operator, sometimes by a manipulator. So it's exposure to hot parts, oil vapors, maybe open flames. Second, it's labor intensive. That requires a person there or a manipulator to conduct hardening for each piece at a time. Also, each piece is exposed to the ambient environment, which means it's exposed to oxygen. So there's risk for excessive oxidation to the part during transfer. And it has an environmental effect in that it could be releasing CO or CO2, and all of the parts need to be washed, which involves washer chemicals. There's also some additional items like the number of pieces of equipment that are involved. There's the reheat furnace, the press quench, the washer, and keep in mind that, as I mentioned, in that press quench there is a die that has to be manufactured for each part geometry, maintained, and replaced after a certain number of uses. So, what alternatives may we have? Instead of using a press quench machine, we can try cooling each part individually in a high pressure gas quench. Okay, why? Well, first, as opposed to regular high pressure gas quenching in batch, this process will allow uniform gas flow around the entire part, unlike the batch process where the neighboring parts will affect the gas flow. Also, rather than just quenching the part statically, it could be rotated to further increase the cooling uniformity. This allows undisturbed flow from all directions, as you will see in this video. As this video shows, this arrangement allows for rapid cooling in a very uniform manner. How? First, the part is inserted into the quenching chamber. It rests on a set of nozzles that then move to encapsulate it from both below and above. These nozzles are arranged in a pattern to allow for as much direct impingement on the workpiece as possible. Then, of course, like a normal single chamber vacuum furnace, this chamber is pressurized to up to 10 bar in nitrogen, and gas is then circulated through a heat exchanger and a fan through these nozzles around the part and back out. In this process, the part cools rapidly, and meanwhile it rotates, further allowing the part to cool in a more uniform fashion. So, to summarize, the part is being impinged by gas from all sides and is moving through that gas flow field, and cooling at the same time. The key process variables are the gas pressure, the gas velocity, the nozzle pattern, the rotation, and time. Now, of course, all these items can be varied and are depending on the part material and geometry. Next question is, what is the effect? Well, as you see from this chart, the net effect is fairly strong. As you'll see here, we have data from a high pressure gas quench furnace where the parts are inserted in a batch into a quenching chamber. So this isn't just a single chamber furnace, it's a two-chamber furnace, and the second chamber is for quenching only. You'll see too that the gases are varied from nitrogen to helium to even hydrogen, and the pressures are varied as well along the horizontal axis. And on the vertical axis, we see the overall heat transfer coefficient, if you will. On the right-hand side, on the vertical axis, we see relative fan speeds. But the point is that if we look at 10 bar with a single piece in nitrogen, we see the equivalence to either quenching in helium at maximum speed and pressure, or we reach the boundary between a medium to fast oil quench, again, just in high pressure gas quenching, but with a single piece. This is a significant impact because we aren't exposing the part to a scenario where distortion will be an issue. So we get the hardenability without the distortion. Now, to be fair, the distortion doesn't disappear, but say in this case of the bevel gear that we've been watching develop through this sequence, the reduction in distortion for variables like the flatness, roundness, or the actual runout, when compared with traditional batch oil quenching, is reduced by up to 2 to 4 times, which is a remarkable decrease in distortion and may just be enough to remove most of the post-heat treating hard machining required to finish the manufacturing process of this part. Looking at a slightly different part in the 6-inch bearing race, we see that in this case the flatness increased by about overall 8 thousandths of a millimeter. And in the case of roundness, only increased 1/1000th of a millimeter. So again, the distortion here is so minimal that we can prevent most, if not all, of the post-heat treating or post-hardening machining, which again is a significant advantage over traditional batch heat treating in the overall manufacturing cost. What does it take to do this? Well, it's typically a piece of equipment that has the ability to move each piece through one piece at a time and then into the hardening chamber. Now, in this case, we'll take a look at the 4D quench technology developed by the SECO work group. And here you'll find that this particular setup can handle a up to 20-inch diameter part that is up to 6 inches high with a mass of up to 40 pounds. This particular piece of equipment would have the maximum processing temperature of 2300 degrees Fahrenheit with a plus or minus 10 degree Fahrenheit uniformity, and using a cycle time of roughly up to 90 seconds, but depending on the part can go down as low as 40, can achieve a throughput of almost 750,000 parts a year. And of course, it has the same quenching capability we've been discussing of up to 10 bar in nitrogen. Now, okay, does it have to be in this configuration? No. This process lends itself to being quite flexible so that it can handle a variety of different materials, different part sizes, and different geometries. Things to consider when changing that, though, are the quench nozzle configurations, which can be configured a number of different ways to accommodate different part geometries. Also, keep in mind that this whole system can be constructed as a cell that can be in line with the other machining processes that accompany it both pre and post hardening. What does this mean? It means less downtime, transporting the parts to a different area within the facility or even to a different facility for heat treating. It can all be done in line at once. Also, unlike the batch heat treating process, each part is treated individually, which means each part can be tracked and traced individually and tested individually. That means the results for each part can be certified for each individual part, not each individual lot. And as we mentioned before, case hardening processes like low pressure carburizing can also be handled in this equipment. And to recap, what advantages does single piece flow really bring to the table? Well, first, as we've spent a great deal of time talking about today, we minimize the distortion. Don't eliminate it, but we do minimize it. It has the ability for high repeatability and precision in heat treating. There's full single part traceability. The entire process occurs in a vacuum, so that means there's no surface oxidation nor decarburization. The parts will come out clean because there's no oil, unlike the press quenching process that we discussed. The whole process can accommodate both lower, more batch-related manufacturing processes with limited parts quantities, or it can handle high production. It can be combined with case hardening while placed in line with other manufacturing processes like pre and post machining. And because the furnace is tuned to handle each individual part, we minimize the additional tooling requirements required by batch processing. Also, the entire process can be automated, and it presents little to no harm to the environment by minimizing the use of detergents and other process gases that could harm the environment. So what does this mean? Overall, we discovered that distortion is a challenge in batch processing. The traditional solution to distortion is press quenching, which is, in and of its sorts, a single piece flow process, but not in high pressure gas quench. When we move to high pressure gas quench, the distortion in single piece flow is reduced by a factor of 2 to 4 times versus typical batch hardening, and that the single piece flow process is flexible and can meet the demands of high production entirely in a vacuum, or it can meet the process demands of batch type processing with some configuration changes. With that, I'd like to take this opportunity to thank you for joining me today, and I hope that you found this discussion valuable and informative. Thank you very much.